Hello and welcome to another video on complex loci, and this is a question I found from an AQA paper. I can't remember which one, 2021 or something. Yeah, it was one which I did with Daniela when she popped in the other day, and I think it's a good example of a complex numbers loci question which actually has some awkwardness to it. I could certainly see this stressing people out in the exam. It doesn't look like a typical sketch a region in on the Argand diagram and then find the minimum value Z or maximum value Z or something like that. My point is these questions can be difficult. So let's have a look at it. Now, I'm going to show you two ways of doing this one. 1 second, I'm just going to close the door because it's really noisy with everybody walking past. 1 second. Sorry about that. So, yeah, what is up with this question? Well, I mean, I look at this, and I'm going to show you the way I did it first, and I definitely did it a slightly longer way, basically because it lured me into it. That's all I can say. It tempted me into doing it the slightly longer way. Because when I look at this, I see loci. That's what I think. I think this is like perpendicular bisectors. So one thing which is stressing me out is the complex conjugate here, whereas it's just a normal number here. Now, the way I approached this was I thought, well, it would be relatively easy for me to work with the conjugate here, because one thing I know about conjugates is that adding or subtracting real numbers to them doesn't make any difference. What I'm saying is, if I was going to work out z minus 3, that's going to be exactly, it's not going to be exactly the same as z star minus 3, because z star puts a negative on the imaginary component. That's what conjugate does. But it is going to have the same size, yeah? In other words, the size of z minus 3 is going to be equal to the size of z star minus 3. And you might not be completely convinced of that at first, so use some numbers. If z was 2 plus 3i, well, then z star is going to be 2 minus 3i. In other words, z minus 3 is minus 1 plus 3i, and z star minus 3 is minus 1 minus 3i. Do you see what I mean? They've got exactly the same real part. And all that's happened to the imaginary part is it's changed sign. So, of course, they're going to have the same sizes, because that's just going to be root 10. And this is going to be, well, if I z star minus 3 there, if I find the length of that, then that's going to be root 10. Yeah. Apologies. I've got a lot happening around me here. There's absolute noise in the corridor outside. Okay, so the first thing I thought was I could easily swap this. I could just say clearly z minus 3 equals z star minus 3. And then what I did was I thought, well, great, I can find where z star lives, because it lives on the perpendicular bisector, yeah? I always talk about where z lives in these kind of loci questions, because the path of points mapped out is where the complex numbers are represented by z, the letter z. Okay, so z star minus 1 plus 2i. And I'm going to show you two ways of doing this, and if you want to go past the drawing out approach, then by all means fast forward the video, but you might need to draw it out, because you never know when a question is going to force you to do something like this. So I did that first, and then I thought, okay, I can easily decide on the Cartesian equation now, because what I can tell you is that, well, 1 plus 2i is kind of there, isn't it? 1, 2, and, this is going to be z minus just 3 here, so that's going to be at 3. So what I first realized was, if I'm working out the equation of the perpendicular bisector for that line, well, what's it going to be? It's going to be somewhere on this line here. Yeah, that's the midpoint of 1, 2, and 3, 0. So that's going to be at 2, 1. Yeah. And what's more, I can see the gradient of this line, because it's going from 1 up to 3, it's going down 2 across 2. The gradient of that line is going to be minus 1. Oh, minus 1. And so this gradient is going to be positive 1. Now I just need to make sure 2, 1 lies on the line. And sure enough, if I have y equals x, well, if x is 2, y has got to be 1. So it's going to be y equals x minus 1. And that's going to be going through minus 1 down there. Good, yeah? Now, the problem is, that's where z star lives, yeah? Now, how do you go from z star to z? You just reflect. You just reflect in the real axis. So now I can easily establish the perpendicular bisector for z, yeah? The perpendicular bisector for z would have been like this, going through 1, because we're reflecting it, and that will go through positive 1. It will have a gradient of minus 1. And if you like, the Cartesian equation of this sign would be y equals minus x plus 1. Yeah? And there we go. We now know that z lies on this line. Yeah? Now, if you notice, the question had this condition, and it also had this condition. Now, I've only dealt with the first condition. Now, they're basically trying to find the minimum and maximum values of A such that both of these two equations hold. Yeah? Now, let's just draw in a separate diagram that line which we've found, as I put it, Z lives on. Yeah? That's this line here. It's got the equation y equals minus x add 1 in Cartesian money, if you like. It goes through 1 and 1. Yeah? Now, if you think about it, if we want A to be real, yeah, in other words, if we want these equations to have complex numbers for which these two hold, then we need the circle which this represents, which is a circle of radius 3, centre A, and as A is a real number, A lies somewhere on this axis, we need the circle to intersect this line twice. So what I did next was I drew a circle, and I figured, well, this will be the most extreme case. This will give me the minimum value of A, yeah? And remember, the radius is 3, yeah? And as that's a gradient of minus 1, that's going to have a gradient of 1, and that's going to be at 90 degrees, yeah? Now, think about what I've just said. I've said that's got a gradient of 1 because that's got a gradient of minus 1 because it's at 90 degrees, which means both of these lengths will be the same, yeah? So if I call them x, I can say 3 squared equals x squared plus x squared. Sorry, I'm getting ahead of myself here. And so 2x squared is 9. And so x equals 9 over 2 square rooted, which is 3 over root 2. Yeah? Now, the point is that's a length, so I'm just going to take the positive amount. But I've now found the length of that and the length of that. Now, remember, actually, this also has a gradient 1. So if that's x, then this is x. So the distance from here to here is x as well. And so I can now deduce as, I'm sorry, it's a bit unclear on my diagram, as that's going through 1, and apologies for how poor this diagram is because it's super useful to this method. I now know the gap from A up to 1 there. And let me just rub that and make that look a bit more like a 1. That's better. So I can now find the distance from A to 1. Now, if you ever find the distance between 2 points on a line, you just do 1 minus the other. So I can see that 1 take away A is going to be equal to 2x, which is 6 over root 2. And I can easily rearrange this to find what A equals. A is going to equal 1 minus 6 over root 2. Rationalize the denominator for the second bit. We're going to get 1 minus 6 root 2 over 2, which is 1 minus 3 root 2. Yeah? And that's the minimum value of A. So how do I find the maximum value of A? Well, a really similar way, but everything's just in reverse on the other side. We're going to have a circle round like this. We're going to have a center here, A. We're going to have that once again as a gradient of 1 because this is minus 1. This is once again going to be, because that's a radius of 3, this is going to be 6 over root 2. Sorry, 3 over root 2. Let's write it down right. And 3 over root 2. I can make exactly the same argument for that gap there. And you get A minus 1 this time equals 6 over root 2. And so you're going to get A equals 1 plus 6 over root 2, which is 1 plus 3 root 2. And so in the end, I can say that the two values for S and T is going to be S is 3, T is 2. Told you S and T were prime, yeah? So that was my way of doing it. Now let's talk about method 2, which is the algebraic approach. This is probably, well, it's definitely what I had in the mark scheme. It probably is a little bit quicker, but it's slightly harder, yeah? If you let Z equal X plus IY, then Z star is going to be X minus IY. Normally I'd choose A plus BI, but they've already used A as a letter in the question, so it's a bit annoying. And then what we can do is we can say, okay, we've got X minus IY minus 1 minus 2I. Well, that's going to be the same as X minus 1 minus IY minus 2I. And then on the right-hand side, we're going to have X plus IY minus 3. Well, let's call it X minus 3 plus IY, just so we can group their real and imaginary. Now, if we had this, we could say, okay, the real parts are just going to be x minus 1 squared plus, and then we're going to have like minus y minus 2 squared. This is how we would find the length of that complex number. Same over here, and so we're going to have x minus 3 squared plus y squared. We can get rid of the square roots, and then we can multiply out the brackets. X squared minus 2x plus 1 plus y squared plus 4y plus 4. Well, that's going to equal x squared minus 6x plus 9 plus y squared. Get rid of the x squareds, get rid of the y squareds. That's nice. We're going to have minus 2x, plus 6x, so that's going to be 4x. Tick when you've done them. Plus 5, but we'll have that as take the 5 off the 9, we'll have it as 4. Little bit of arithmetic problems there. And then we've got plus 4y, and so we've got x plus y is 1. Yeah. Okay, and that's good news. Okay, what else have we got? Well, we haven't worked with the second condition yet. Let's work with this algebraically. So we've got, now remember, z is x plus iy, so we're going to have x minus a plus iy. Well, the length of that is equal to 3. And so we can say x minus a squared plus y squared is equal to 9. Yeah, and we've got two equations. Yeah, now we can eliminate. We obviously don't want this to be anything to do with x or y because we want everything in terms of a. Yeah, so let's get rid of y first. Now we can see that y is 1 minus x, so I could say that x minus a squared plus 1 minus x squared is equal to 9. And so I can then deduce that I've got x squared minus 2ax plus a squared plus 1 minus 2x plus x squared is equal to 9. Now, what am I doing here? Well, I'm really not interested in x. I'm interested in a. And I have a quadratic in a here because I've got a squared minus 2ax. And then I've got tons of junk on the end because, let me just tick the ones I've done. X squared minus 2ax. Then I'm going to have minus 2x plus 1 plus 2x squared minus 9 equals 0, yeah? Now, what do I know about this quadratic in A? Well, I know that if A is real, yeah, then it needs to have at least one repeated root, yeah? And so what I need to have, therefore, is b squared minus 4ac is not equal to 0, but greater than 0, yeah? Now, what's b squared here? Well, b squared is going to be, okay, right, let's, should we treat this as a quadratic in A or a quadratic in X? I need to treat this as a quadratic in X, I'm sorry. The reason why I want to treat it as a quadratic in X is so I've got A in my answer. That's a really good reason. So let's group this as 2x squared. It's also much nicer to do. Plus x times 2a, 2 minus 2a. Yeah, I've done that one and that one. And then I've got plus a squared minus 8 equals 0, yeah? Now, I know that for x, I want, because x is this number here, I need x to be real, because by definition, x was a real number here, because it represented that complex number. And so this should have two real roots. And at that point, b squared minus 4ac is going to be, yeah, and sorry, greater than or equal to 0, yeah, for two real roots. I can have one repeated, yeah, it doesn't matter if it's distinct or not. So let's use b, that's 2 minus 2a all squared. There we go, we keep a in it. Minus 4 times 2 times by a squared minus 8 is greater than or equal to 0. Okay, multiply it out. We're going to get 4a squared minus 4a minus 4a, well, that's minus 8a, and then plus 4. Then we get minus 8a squared plus 8 times 8, which is 64, is greater than or equal to 0. Okay, right, what do we end up with at the end? We get minus 4a squared minus 8a plus 68 is greater than or equal to 0. I might multiply this all by, divide this all by minus 4. I'm going to get a squared minus 2a minus 68 divisible by minus 4. Yes, it is. 17. Don't forget to change the sign on that, change the sign on that, change the sign on that, and change the inequality round, yeah? Okay, we'll solve this by completing the square. A plus 1 squared minus 1 minus 17 is minus 18, is less than or equal to 0. Now, when you're solving a quadratic is less than or equal to 0, that gives you this situation. And so we want it bounded between two values. Actually, the graph's going to look more like this. Yeah, for that quadratic. Okay, and when we're solving it, if we just consider equality, because that will give us the two critical values, I'm just going to put consider critical values so the examiner knows what I'm doing. A plus 1 squared minus 18 equals 0. So A equals, well, you're going to add the 18 and square root it. And that's going to have a plus or minus, and then you can put a minus 1. And so what are we going to have here? We're going to have A equals minus 1 plus or minus 3 root 2, which is, of course, the same as 3 root 2 minus 1, or minus 3 root 2 minus 1. Is that the same answer I got before? Is there a sign error somewhere? 1 minus 3 root 2 and 1 plus 3 root 2. So I think it should be a positive 1. Clearly made a mistake somewhere. Where was my mistake? 4a squared minus that divided by that. Change that round. That's good. Is it up here further? X squared minus 2ax. X minus a. Is it x minus a? It should be the other way around on this one, actually, shouldn't it? So minus 4a is minus 8a, but I'm dividing it through by minus 4. Is it up here? Oh, yeah, I've seen it. Look, minus 2ax minus 2x. So there we go, a sign error. How frustrating. You would be able to tell that in the exam, I would like to point out. And this is part of how we get the right answer, isn't it? Because this is positive 1 and positive 1. So you get little hints in the thing. But yeah, apologies for me making that mistake. I'm just going to feed through the error. This is an important skill. This is now going to be the same as that, which makes things significantly nicer because that's going to be a plus, which means that's going to be a minus, which means that's going to be a minus 1, and we end up with the correct answer. Yeah, error correction, it's part of the game, remember that. So yeah, and I wanted to show you both ways of doing it. This is the way the mark scheme did it, so you may well feel more comfortable doing it like that, but it's not the way I first noticed. I just thought this looks like a typical loci, complex loci and a plane question to me, and so I did it with these funny little diagrams, and those diagrams come in really useful. So yeah, I hope this video is useful. You know, always try these questions before I give you. I'm going to keep putting up videos in the next few, in the next week or two. If always try and do the question first is my advice, otherwise you don't get so much out of it. But I'm picking questions now as well, obviously. I'm not picking the run-of-the-mill questions. I'm picking ones which are as nasty as possible. Ones which I think could easily upset you in exam conditions. So hope it helped, and all the best. Bye-bye.